Hello, and welcome to another lecture. So today we're going to start looking at harmonic functions and really just these basic um, ideas about harmonic functions. We're going to define those, and we're going to show that they're actually the real and imaginary parts of holomorphic functions. So this is subsection 7.1.1 in the book. So this is the first subsection in chapter 7. And you can get the book in the link in the description. You can get it as a free PDF, or you can buy a cheap paperback. All right. So, what are harmonic functions? So, suppose that we have an open subset of the plane, and we're going to stick with the plane. There are harmonic functions in any number of variables, but we're just going to study the harmonic functions in R2, basically in C. So, let U be an open subset of the plane. And then suppose that we have twice real differentiable, so we want at least two continuous derivatives, real valued function. Then this f is harmonic if it satisfies Laplace's equation. So if the second derivative in x is the real part plus the second derivative in y, if they sum to 0 on u. Right? This operator, nabla squared, sometimes it's written as delta. It's called a Laplacian. And so if the Laplacian of f is 0, we say that f is harmonic. Now, maybe a little note about the R. So sometimes people talk about complex valued harmonic functions, and those would be the functions whose real and imaginary parts are harmonic in this way. But we're going to stick to real valued, because we're really interested in the real and imaginary parts of holomorphic functions. So those are real valued functions, and it really makes a lot of sense to stick to real valued functions. Because we're gonna, there's a lot of the results that we proved are for real valued harmonic functions, and you can really just study those. All right, so that's what we're doing. All right, so now let's write the Laplacian in a different way. And the way to write it, I mean, it's not a terrible way to write it, but it's a sum of two of these partial derivatives. Now it's much better, and I'm gonna remark on that later on again. It's much better to write something like this as just a single double. I mean, it's mixed, but single double derivative, right? That we differentiate in z and z bar. Okay, these are the Wirtinger operators. They're not really, derivatives in the very traditional sense, but yeah, they act like derivatives, right? So if we take this operator where we take the z derivative and then the z bar derivative f, and we're going to multiply by 4 just to make things work out, just because of these halves, right, out here. So the 4 cancels that out. So this is what that really is, right? And well, if you work it out, you're going to find, well, because it is plus and minus, the cross term just cancel out. The 4 cancels out the halves. You get precisely the Laplacian, right? So this is another way of writing the Laplacian. And again, the 4 doesn't matter because we're looking at where this is 0, right? So, so what does this say? This says that f is harmonic if the z derivative of f is holomorphic, right? And by this I mean the Wirtinger derivative of f, the z derivative, right? So really, I'm looking at this function over here, right? So I take the z derivative of f, and then because we're taking the z bar derivative and that's 0, well, then this guy is holomorphic, right? So we can see that that's equivalent. That the f is harmonic if and only if the Wirtinger z derivative of f is a holomorphic function, right? So suppose that we have a harmonic function. So locally, we can, because this dftz, that's a holomorphic function, we can locally find a primitive. Maybe not globally, but locally on any, any small neighborhood or any simply connected domain, if you recall, we can find a primitive. So some function, some holomorphic function g, whose derivative is dftz, right? Whose now actual, honest to God holomorphic derivative is dftz, right? So, so let's see this function c. Let it be f minus g, right? And by the way, do notice that the primitive is not f, of course, right? Because it's supposed to be a holomorphic primitive. So this is not identically 0, right? But if I take, well, first it's c2. I can take, I can take derivatives. But the point is that if I take the z derivative, well, that's just taking the z derivative of f minus the z derivative of g. Now, the z derivative of g is just equal because g is holomorphic. F is not holomorphic. I can't say anything about that. But the g is holomorphic, so it's the derivative. It's actually just its regular derivative. And I know that that's dftz. Therefore, it's 0, right? So we have that the z derivative of c is 0. All right, so let's bar c. So let's take the complex conjugate of c. That's really what we're interested in. So if I take the z bar derivative of h, right? So that's really the z bar derivative of c bar. So if you work out what that means in terms of diverting the derivatives, that's the bar, the complex conjugate of the z derivative of c, and we know that that's 0, right? Okay, so that means that h is holomorphic, right? All right, so what did we do? We wrote, if we write f, if I solve for f, right? So f is g plus the bar of c, right? Sorry, the bar of h, which is c, right? This is c, right? So we have f written as a holomorphic function plus the complex conjugate of a holomorphic function. Now we can do better than that. So let phi be g plus h. And we know that f is real valued, right? So f is equal to its real part, right? And so what is the real part? I take the function, I add its conjugate, right? And I divide by 2, right? That's just how I compute real parts of things, right? Well, I can reorder this and put the non-bars on one side and the bars on the other side, right? And I notice, well, that's just phi, right? This is just the real part of phi, right? So what we have is that we wrote f as the real part of a holomorphic function. Now locally, right? Or we could do it in a simply connected U. So locally you can always find a simply connected neighborhood. Just take a disk, right, around the point. So locally, it's basically wherever we could find this primitive g, right? And we know that we can do that on simply connected domains, right? All right. So what did we do? So if we have, maybe let's write it more generally. So or more precisely, I mean. So if we have a simply connected domain and a harmonic function, then there exists a holomorphic phi on that simply connected domain such that f is the real part of phi, right? And similarly, we can do it with imaginary part, right? You can you can figure out how to make it the imaginary part of a holomorphic function, right? Now, we can go backwards as well. So suppose that that f is the real part of a holomorphic function. That is, it's 1/2 of phi plus phi bar, right? Well, then notice that the Laplacian, well, if I write it in terms of the z's and the z bars, well, these guys commute, right? I can take the z derivative first, and then the z bar derivative, or the z bar derivative, and then the z derivative. Now, that's useful if I apply it to this thing, because I'm applying it to a holomorphic function and a bar of a holomorphic function, right? So I'm applying this this operator to this thing and then to this thing. Now, if I apply it to the phi, I want to apply the z bar first, because then this whole thing is 0, right? Because I'm taking the z bar of a holomorphic function. But if I'm applying it to phi bar, then I want to do the z first, z derivative first, because then phi bar is anti-holomorphic. Its z derivative is 0, right? So we get that this is 0, right? So basically, what we have is that what we proved, that if it is the real part of a holomorphic function, it is it is harmonic, right? All right, so let's summarize this in a proposition. So suppose that an open U and a function f. So the function f is harmonic, meaning it's C2 and satisfies the Laplace equation, if and only if for every p there is a neighborhood and a holomorphic function in the neighborhood such that f is the real value of phi on p, right? And this is an if and only if, right? That's what we proved, basically, right? Now, another way to basically state the same thing is that it's harmonic, f is harmonic, if and only if around each p there is a power series expansion of the following sort. Now, it's not a power series expansion in just z minus p. It's a power series expansion in z minus p and z minus p bar, but of this very specific form. We're never multiplying z minus p and z minus p bar, right? So it is a very special, really real power series in two real variables, and we can write those in terms of the z's and the z bars. But it's this very special power series, right? And we know that this converges actually uniformly, absolutely on every closed disk. Well, why? Because we can find these holomorphic functions and their power series, right? This is really, these two bits come from the power series of phi and the phi bar, right? And we know that the power series converge on, we can always define them on any disk, right? Because that's simply connected, right? All right, so we have this this if and only if, right? Or two ways of writing this if and only if. All right, now one corollary of that, which is immediate, is that if I have a harmonic function, then it's actually infinitely real differentiable, right? I mean, it's the real part of a holomorphic function. Holomorphic function is infinitely differentiable, real differentiable, complex differentiable, right? Both. This one is only real differentiable, but yeah, we get infinitely many derivatives, right? So even though we started with, we just assumed 2, we automatically get get all of the higher derivatives as well, right? So any solution to the Laplace equation is infinitely differentiable. All right. So suppose that we start with a harmonic function, and suppose that we have another harmonic function such that f plus ig is holomorphic, right? Basically, we know that harmonic functions are real parts of holomorphic functions. So, g is that imaginary part, right? So we give this a name. We call it the harmonic conjugate of f, right? So every harmonic f on a simply connected domain has a harmonic conjugate because I can find it as a real part of a holomorphic function. However, if I look on something that's not simply connected, then it's not necessarily true. So, for example, on c minus the origin, the punctured plane, if I look at log of the mod z, which is the real part of some branch of the logarithm, so it's harmonic. Well, locally, it's it's the real part of a branch. I mean, I don't have a branch defined globally, but near any point, I have a branch of the logarithm, and log of mod z is the real part of it. So, so this is harmonic, but there is no harmonic conjugate because if we did have a harmonic conjugate, then we would get a branch of the logarithm inside the in the punctured plane. Now, it's maybe not completely immediately obvious, so let's give the proposition of why this works, and that's because if we have two harmonic conjugates for f, and they're not unique, we can have two different harmonic conjugates, but they differ by a constant, right? Well, suppose that we're on a domain. If it's disconnected, they might differ by a different constant on different components. So let's just suppose that we're on a connected open U, right? So then if we have two harmonic conjugates, then they differ by a constant. And the proof is not hard. If we take a look at this, right? So I take f plus I g1, which is that's holomorphic, right? Same f plus I g2, that's holomorphic, right? And if I subtract those two and I divide by I, right, I will get g1 minus g2. Now that's real valued, right? Because g1 and g2 are real valued. But this thing is holomorphic, right? Because it's just the difference of two holomorphic functions divided by I, right? That's holomorphic, right? So you have a holomorphic function that's real valued. That means it has to be constant, right? So that's the C. All right. So the real parts and imaginary parts of holomorphic functions are harmonic. But the modulus is not, right? I mean, if we think of how, the three different ways of getting real numbers out of complex numbers, the real part, the imaginary part, and the modulus. Well, the modulus is not harmonic, but it's not, we don't want to lose hope because log of the modulus of f is harmonic. Well, you have to avoid the places where f is 0, right? So you avoid those isolated points where f is 0, right? And there, of course, this is not defined, but everywhere else, this is a nice harmonic function, right? So you have the real parts, the imaginary parts, and the log of mod z are your sort of the three different ways of getting harmonic functions out of holomorphic functions, right? And so, depending on what you want to talk about, any one of these might be useful. So, this is an exercise to show that that's true, right? It's anyway. I'll let you work it out. So it's it is harmonic, right? Okay, so and that we're talking about exercises. So another exercise is that you can actually go backwards in that proposition, right? So if you have a harmonic function, then you can locally find a holomorphic phi whose log of mod phi is equal to f. All right, so another exercise, another useful exercise is that suppose that we have a holomorphic function between two domains, u and v. And suppose that we have a real valued function on v, then this real valued function, and suppose it's harmonic, then if we compose this real valued function with f, so f goes from u to v, and g goes from v to r, right? So g composed with f goes from u to r, right? So it's a real valued function, then this is a harmonic, right? So holomorphic functions preserve harmonic functions. And related to that is that if f is actually a biholomorphism, then and that just follows from part A, or you should be able to prove it from part A, is that G is harmonic if and only if G composed with F is harmonic, right? So you can check for harmonicity on either the source or the target, on U and V, right? And biholomorphic functions just completely preserve the set of harmonic functions. Now, this is, harmonic functions come up in applied math even, right? Because the Laplace's equation, that's it's like steady state heat is the solution of a Laplace equation, or maybe the electric potential around the charged object. That's a harmonic function. So it's solving the Laplace equation in various domains is actually an applied math kind of thing. And this says that you can do biholomorphisms, right? So we know the Riemann mapping theorem, for example. So if you figure out how to solve solve the Laplace equation in a disk, right? Like the typical thing that we'll actually look at is suppose that we have boundary values, so values on a circle, and we want a harmonic function inside with those boundary values, right? Well, then this says that this solves it in any simply connected domain, right? Well, it was nice enough boundary so that you can still talk about boundary values, but basically, if I have a square now or some more complicated thing, as long as I can find that biholomorphism, I can solve the Laplace equation in a more complicated domain just by solving in a disk, which is rather simple, as we'll see. All right. Now the next useful exercise is prove the Liouville theorem for harmonic functions. So it's slightly different. So suppose that we have a harmonic function on all of C, but instead of bounded, we're going to say, well, suppose it's non-negative. Then f is constant, right? So suppose this is never negative. Basically, suppose that we have some inequality. There's this change in the Liouville theorem, goes from bounded for holomorphic functions to non-negative for harmonic functions. Why is that? Well, if f is holomorphic and bounded, then if I take the logarithm of if I add m to it, right, sufficiently large m, then I can make this guy non-negative, right? Basically, I can make it. I can make f of z plus m sort of sufficiently far away from 0 for all z, right? Because it's bounded. F is bounded, right? And then log of mod of that is going to be positive. And then the same thing was the real part. Vice versa, if we have that log of f is non-negative, then 1 over f is a bounded function. Or if I have if my function is the real part of f, right, and if that's positive, then this expression, I apply this linear fraction that basically takes the upper half plane to the disk. So that's bounded, right? Because this says that f is valued in the not upper half plane, the right half plane, right? So if it would be imaginary f, which is also harmonic, that would be the upper half plane. But then there would be a different linear fractional. All right, now here's that remark that I made. I talked about in the beginning. Now this idea that we rewrite this the Laplacian, if I add the two second derivatives, rewrite it as a single mixed second derivative, right? So differentiating one variable and then in the other, so that then you can integrate twice, right? That's what we did. We found, right, found the primitive, right? So that might sound familiar. You might have seen this before in a previous class. Maybe you did, maybe you didn't. So let's talk about it. This is the D'Alembert solution to the one-dimensional wave equation. So the wave operator is this guy, and I'm using x and t for sort of to be traditional rather than x and y, because t is time, x is position, right? And the wave operator is then this thing. So here the difference is, I mean, other than that, it's just changing variable names, but there's a minus sign, right? And so if there's a minus sign, what we can do is we can change it into these guys, right? Composition of these two operators. So that's sort of like z and z bar, but now without the i's, right? And without the constants, so without the halves, right? So that I don't need the 4. So if we change our variables to, we're going to write mu and eta, x plus e and x minus it, right? Then what we get is these are the characteristic, so-called characteristic coordinates. What we'll get is that this guy is actually going to have a minus sign, but it's this this operator, right? The second derivative in mu and eta, right? If I do this change of coordinates, right? And then basically what you do is you integrate twice. So let's not do that, but you integrate twice. You get, basically you're doing precisely the same thing as here, but now these guys are nice real variables instead of these weird Wirtinger sort of things, right? These are actual, honest to God, the derivatives, and you can solve just like before. We got that it's a function of z and a function of z bar, right? It was a holomorphic function and an anti-holomorphic function. We get now that it's a function of mu plus a function of eta, and we just write these, put the x and the t back. And well, what that says is that the solution of the wave operator is two waves traveling in opposite direction, right? You have the wave A, and all I'm doing as time goes on is I'm shifting it, right? And I'm shifting B in the opposite direction, right? So I have two waves, they're superimposed, so I'm adding them, and they're traveling in two different directions, right? I mean, if you remember, if you take a long string, put some slack on it, and you can flick it a little bit, you'll see a wave traveling along the rope, right? That's precisely the wave equation, right? It's the same wave, and it's traveling. It doesn't change. It's basically the same. Well, ideally, it doesn't change. Of course, there's friction and whatever, like it's going to dissipate a little bit, but in ideal circumstances, a one-dimensional wave equation, you're just going to get that wave traveling across, right? I mean, that's how like all communications work, right? I have a wire and I send a signal across, and it's just the same signal, just a little bit later, I'll find it on the other side, right? And it shouldn't just be sort of all different. I mean, I have the same function, just shifted, right? And well, if it's electric signal, it's very fast, right? But you could do sound waves, right? That's if I do sound waves in a long thick tube, well, not very thick, thin tube, right? If I talk into it, or maybe with the two cans and a string in between them, right? Then we're doing precisely the one-dimensional wave equation. All right, so that's moving into a completely different thing. All right, so next time we're gonna talk more about harmonic function. We're gonna look at 712. All right, so see you then.